Yeah, hello everyone. Today's lecture I will continue optical waveguides theory and design. Specifically, I will be considering slab waveguides design solution. Of course, I will be discussing at this moment based on total internal reflection principle, and for that I take one example of silicon on insulator. In the previous lecture I have shown that different device layer, different type of wafers we can use for different application purpose, but for today's discussion I consider silicon on insulator. Typically it is called in short you can call it as a SOI, silicon on insulator. So, as I already told you before that this silicon on insulator wafer nowadays available up to good quality optical grade silicon on insulator wafer can be available up to 3 millimeter diameter. Okay. But here I have shown a piece of SOI sample. It can be diced from a full wafer, and if you diced that you can see clearly 3 layers. So, layer 1, layer 2 and then layer 3. Okay. The first layer is a thicker one, that is actually silicon substrate called handle wafer. It has no role in optical waveguide design, but it gives mechanical strength to the wafer. If you are fabricating a chip out of SOI, you can get a good strength if you have this much thickness. That is the reason this much thickness is given as a silicon substrate, just a handle wafer. And then you have a buried oxide layer 2 to 3 micrometer typically. It is basically silicon dioxide, and then in the top that is the actually your device layer called silicon on insulator. This is the layer called SOI. Silicon, this is silicon basically, this is a basically silicon crystalline silicon on insulator. Insulator is silicon dioxide, and thickness depending on your requirement you can control the thickness. Typically it is 220 nanometer, is very popular in foundries nowadays for photonic integrated circuits, but it can be customized to 100 nanometer and can be thicker 1 micron 2 micrometer device layer. Fine. So, this type of SOI wafer I will be considering, SOI sample I will be considering while discussing the design aspects of a slab waveguide. Okay. Since the substrate handle wafer that is not useful for guiding purpose, so I removed in this picture. I just consider only box, that is actually silicon dioxide, and that actually act as a lower cladding of the slab waveguide, and then this device layer actual core where actually light will be confined, and in the top if you do not do anything, that means it is air. Okay. So, air also you can consider as a refractive index, you can have dielectric material with a refractive index N3 equal to 1, and N1 here if you just think of silicon crystalline silicon, the refractive index 1550 nanometer wavelength at 1550 nanometer, which is the communication band, third generation communication band, optical communication band. And we know that any dielectric material or conductor or whatever you can actually represent refractive index in complex form, which has a real part is the actual refractive index, and then imaginary part is called the extinction coefficient or kappa. And at 1550 nanometer, as you know, this is a photon energy sufficiently low and band gap lower than band gap of the silicon crystal, that is why it is transparent, that is why you only see the real part of the refractive index. So, imaginary part is 0. So, that is transparent around 1550 nanometer, this typically above 1.12 micrometer wavelength it is transparent. So, that is actually shown. So, that means we are now set with N1 as 3.4778. Okay. Now, silicon dioxide, this is the silicon dioxide box layer you are using. Box layer also if you consider the same communication wavelength 1550 nanometer and refractive index, the real part is about 1.4657. I have just used 4 decimal point, because most of the photonic devices you consider the refractive index change even up to 4th decimal point, that is very important, useful. And kappa is also 0, transparent. Silicon dioxide typically it is almost transparent if it is good quality, particularly if the silicon dioxide is native oxide grown on the silicon, that is quite good quality. So, there would not be any loss or absorption at 1550 nanometer wavelength. Good. So, now you can think of in the top layer you can also have silicon dioxide. You can grow silicon dioxide, then you can have, we can call that is a top oxide layer, that can be also 2 to 3 micrometer. So, that will act as a top cladding layer. So, instead of air you can have top cladding layer also, refractive index of this one around 1550 nanometer. So, in this case if you see tox and box both are silicon dioxide, this is also silicon dioxide, this is also silicon dioxide. So, in this case the core is, that is SOI device layer, is sandwiched between 2 dielectric material, that is silicon dioxide, and they are same basically. That is why this type of slab structure can be considered as a symmetric slab waveguide. Okay. So, because N3 particularly N2 equal to 1.4657, N3 also 1.4657. So, that is why it is symmetric planar waveguide structure. And then sometimes it is useful for a special application purpose, instead of silicon dioxide in the top as a tox, you use silicon nitride also, that is also CMOS compatible. You can deposit silicon nitride, and silicon nitride refractive index is higher than your silicon dioxide, N3 equal to 1.9968, close to 2. So, that means your N2 is silicon dioxide and N3 is your silicon nitride. So, top cladding layer refractive index is more. So, we can consider that N1 greater than N3 greater than N2. Okay. N3 is greater than N2, that is reverse when you are using air, that is N1 greater than N2 will be greater than N3. Normally top if it is air, that is N3, that refractive index will be lower, but in this case it is upper cladding is higher refractive index compared to lower cladding. Okay. So, this can be also acted as a this can be considered as a planar waveguide structure. Cool. Now, so that's I just come back to the if top layer is exposed to air completely, then we just, as I mentioned, N1 greater than N2 and greater than N3. For some calculation purpose, we will be considering this type of asymmetric planar waveguide structure whenever necessary. For symmetric, most of the time whenever you are fabricating photonic circuit, top layer will be oxide coated. So, in that case we will be considering N2 equal to N3, but occasionally if you want to use the top layer as a air, you can just remove oxide layer in that particular area, so that you can design your waveguide structure asymmetric with asymmetric SOI structure. Cool. So, now let us move on. So, we have the I just instead of that 3D view, I just take the vertical direction. So, along x direction intersections are given, because yz plane is infinitely extended, you can consider with respect to your guiding light in the core, and you can consider that along x direction you have your lower cladding will have refractive index of N2, that is x less than or equal to 0 you can consider, and core region should be stretched between x equal to 0 to d with a refractive index N1. N1 means this one, refractive index 3.4778. All the refractive index value I have just given here, they are at lambda equal to 1550 nanometer, third generation communication window. Okay. And N3 we can consider air for discussion purpose. Good. Now, we just already whatever we have already discussed earlier for a slab waveguide, how total internal reflection helps to confine a light in the core region, and these are the governing equation we have discussed in the previous lecture. I have just pulled them here just to continue our discussion and analysis. You know, we can consider one of the two polarizations, TE polarization, where electric field will be tangential to the interface, that means along y direction oscillating, and magnetic field will be in the xz plane, that is called TE polarization. And alternatively you can consider TM polarization, other type of electric field components, where E field is in the xz plane, x component, z component will be there, magnetic field will be the along y direction perpendicular to the screen. Okay. So, one of these two or both you can consider. If any electric field direction, if it is oscillating, you can decompose into these two different type of polarization. You can treat them differently, because this will help us to exploit the boundary conditions at the interfaces, upper interface and lower interface. This is the upper interface, this is the lower interface, and to get the Fresnel reflection and the phase change at total internal reflection, that expression we have derived using these boundary conditions. So, if this is the condition, then we know that TE guided modes can be expressed, electric field can be expressed, only y component will be there and x dependent confinement will be there, okay, and e to the power j omega t minus beta m t e z, that is the field, and beta is the something basically longitudinal component of the wave vector, which is nothing but 2 pi by lambda n 1 sin theta t e and 2 pi by lambda this n 1 sin theta t e is called n effective for the T polarization. Similarly, we can consider for TM polarization, and in case of TM polarization we are considering only HY component. So, I have just same way I put for TM polarization, this y vector, y unit vector is there, a y unit vector along y direction, and magnetic field will be x dependent, because light wave will be confined along x direction, and phase also instead of beta T e, it will be considered as a beta T m, and accordingly n effective also for TM polarization. M is actually called so called your modal index. So, order of the mode, guiding mode. How that is decided? That is decided by the eigen solution, eigen equation. For top one is for TE polarization. This is basically your transverse component, so k1 x, and beta z actually defined by this beta z actually defined by k1 z. So, if wave vector is there going back and forth with total internal reflection, so z components, longitudinal component along that direction, that is actually known as beta, and transverse component you will have plus and minus, that is why standing wave will be there. So, round trip phase 2 times d, so k1 x multiplied by 2 times d, that is the total phase, and this total phase, and you have to also add the phase change upon total internal reflection in the so called lower interface, and phase change corresponding to the upper interface, and these two should be minus sign here, I have taken this side. So, this is one eigen solution. Likewise, you can go for TM polarization. So, their difference only this n 2 and n 1 will be interchanged, numerator and denominator in tan inverse function, that will be interchanged, n 1 by n 2, here n 1 by n 3 in the top interface. So, this equation we have derived from Fresnel's equation, and we have discussed little bit detailed in previous lecture. I have just summarized in this slide to progress to continue our discussion for today's lecture. Okay. Now, let us focus only on TE polarization. So, because you know the equations are almost identical, if you know how to solve in one polarization, you can easily solve for the other polarization. I will discuss only for TE polarization, where electric field component is our concern, that is actually easy to handle, and other components we can easily derive from your Maxwell's curl equations. Once you know electric field, then magnetic field, they are related through Maxwell's equation in frequency domain. Okay. So, in that case, I just repeat that equation for TE polarization. Instead of entire phi expression, I just put that this phi lower, that means phase change happening at the lower interface due to total internal reflection, that must be theta dependent. and upper also theta dependent. So, if you solve this equation for a given value of m, you can get a solution for theta, that is theta 0. If m equal to 0, you will get solution for theta 0, m equal to 1, you will get theta equal to theta 1, and m equal to 2, you get theta 2 and theta 3. So, all these discrete theta solutions you can get if you can actually solve this equation. It is not so easy to solve this equation because it is a transcendental equation. So, you cannot really derive expression. For example, you cannot write something like that theta m equal to something m plus so on something right hand side without theta. So, then it would have been easier, you could calculate easily. But this is transcendental equation, we have to go a little bit different way. I will discuss that today also, then how to. And I have just, instead of phi L writing here, I just put down here for your memory purpose. If the equation it is seen again and again by you, then it can be memorized, so that you can utilize any time for any problem solution. So, couple of more things you should get a knowledge here. If you try to see what is the critical angle at the lower interface, critical angle at the lower interface, that should be lower interface n2 n1. So, sin inverse n2 by n1. So, we can calculate critical angle for the lower interface. I know what is the value of n1 in silicon on insulator platform. So, it will be soy silicon 3.4778, you know that, you can easily calculate, and this one 1.46 something like that, and then it will be air. So, n3 equal to 1. So, n1 you know and n2 you can find out. So, you can get critical angle n2 by n1, right, n2 by n1, that is 1.4 by n1, that is correct. Yeah. And similarly, I can find also theta cu for the upper interface, critical angle for the upper interface. And one thing you must be knowing, that total internal reflection ensure that if the angle theta, whatever solutions you will be getting, that must be greater than the critical angle of the both interface. In this case, you know that theta, this is n2 is greater than n3, that is why I can easily say that theta cl is greater than theta cu. So, that means theta cl greater than theta cu, that means your theta m solutions must be greater than theta cl at least. If it is greater than theta cl, that means it is obviously greater than theta cu. That means, if you get a solution which is greater than theta cl, that ensures the total internal reflection in both the interface. If you are getting a solution which is actually showing something theta m, maybe it is greater than theta cu, but less than theta cl, then theta m, since it is less than theta cl, in the lower interface total internal reflection will not take place. So, it will be leaked out. So, it will not be guiding. So, that information you should be remembering all the time. Okay. Now, you see, now as I said that we can actually find the propagation constant and longitudinal direction, typically k1 and sin theta m, and k1 is nothing but the wave vector in homogeneous medium n1, that is 2 pi by lambda n1, that is k1, and sin theta m, that is actually k1 jet, and that we are defining as a beta. And if I am putting theta m, then I will write beta m, because theta m is discretized. So, beta m also will be discretized, and this n1 sin theta m we separately call it as n effective m. That means, effective index of the mth guided mode, and beta m is the propagation constant of the mth guided mode. Okay. This is the expression we can write. Okay. And what is new here? So, this equation, all the theta m, I have not used anymore this T or Tm something like that. We just keep in mind that we will be using this phi expression, this expression, this is only for T polarization we are using. Okay. Because T to Tm polarization, the difference only in this phase term. This phase term, T polarization will be one expression and Tm polarization will be other expression. Simply it will be instead of n2 by n1, n1 by n2 and n1 by n3, that is for Tm, otherwise the same. Fine. So, good. Next, if I try to see what is the solution for the guided mode. So, I will see that because it is a mode, so I can expect that there will be a good confined well defined distribution along x direction, because along x direction you get a total internal reflection here and you get a total reflection here also. TIR happening here and TIR happening here. So, that means your electromagnetic wave is confined within the core region, right. So, you can get a just a good well defined x distribution, and that particular distribution depends on m. I will discuss that, and the phase, that particular distribution will have a particular solution for beta m, and that will propagate along z direction with this phase parameter omega t minus beta m. Obviously, if this is the phase for a travelling wave, the velocity, phase velocity you can write for mth mode will be omega by beta m. So, once you know n effective m, beta m, and you know the frequency 2 pi c by lambda, that is actually your omega, then you can find the phase velocity for that particular mode. Once you get a beta m, you can find what is the phase velocity it will be. Okay. Now you see, I want to see what is this, what would be this distribution in x less than d greater than equal to 0 in this region, and when x greater than or equal to d and x less than or equal to 0. As I know that this function in this region, it is a standing wave type things. So, standing wave you can represent in terms of cosine or sine function, right. So, cosine and sine function we can write like this. Here I have written kappa 1 m, because this is related to mth mode. Mth mode, how it will be derived? You have some kind of amplitude am1 you are writing, okay, and then cosine kappa 1 m x phi f, some phase I have just added. What is that kappa 1 mx? That is nothing but it is k1 x component for the mth mode, which is nothing but k1 cosine theta m. So, k1 sin theta m is the beta contributing beta, k1 sin theta m is contributing beta, and k1 cos theta m, that is actually this direction standing wave it is creating. So, standing wave you can have e to the power I k1 x plus e to the power minus I k1 x. If you are just considering this thing, one forward propagating wave and another backward propagating wave, obviously they can be multiplied by e to the power j omega t and so on. If you just add them together, what you will get? You will be getting plus plus. So, it will be, you will be getting cosine 2 cosine k1 x time x. So, this will be the value. So, this 2 can be absorbed in the amplitude. So, it is basically cosine function. So, this kappa 1 is nothing but this one, kappa 1 m x, and we can add phi, little bit of phase can be there, so that I can find out what would be the value, because when you put x equal to 0 you can get some value. What is the value here? We can find, we can add some phase if it is there. We have to solve that value by utilizing the boundary condition I will be discussing later. Good. So, this is your solution, standing wave solution along x direction within this region. But what happens in this region or in this region x less than 0? So, you know x less than 0, the x component x direction field should be decaying, because I know that this k2x is imaginary, and since it is imaginary and you do not have any standing wave type of things, only k2x, only this direction it will be there. In core region you have k1x plus and k1x minus standing wave because of the total internal reflection, but when x less than 0 you have only k2x in this direction. So, it is like travelling wave, but once it is imaginary you will see some kind of attenuation, exponential decaying. But here k1x, it is a real value you will be getting, as long as theta m is real, k1 is real, k1x is real. So, you get this thing, but once it is imaginary, if you put this imaginary value here, one more k1x is imaginary, k2x for example, e to the power if you just write j k2x, and if k2 is a imaginary, then you can write minus k2x x. So, this is the thing. So, it will be as a function of x, it will be decaying, that is what we have written. Similarly, it is in the this direction. So, that means this is your solution, this is your entire mode solution, but this entire mode solutions, you know what is the nature in the core region, in the upper cladding region and lower cladding region. And since it is only y component is there in the electric field, so tangential, so I can write, I can find out these constants by utilizing boundary condition, because I can say that Em x equal to d, Em x equal to d this side, for when I am using this one at x equal to d and this one also x equal to d, both are valid at x equal to d, these are two equations. Just x equal to d I will be putting here, x equal to d I will be putting here, then I can get one equation. Similarly, I can say that this equation and this equation, they are same, they should be satisfying because of the boundary condition at x equal to 0. So, if I put x equal to 0 here, x equal to 0 here, you will be getting another equation. In this way, using those equation, I can find what is the relationship between M1, AM2 and AM3, and also I can find the phase value also, phase phi f there. So, once I solve all this, I can consider the AM1, this one, this value whatever you are getting, that can be just normalized to 1. Then I, with respect to that, I can find out using boundary condition what is the AM2 value and what is the AM3 value. Okay. So, once we get that, then we can also find phi f. So, in this way I can actually get what is the field distribution along x direction, that is the mode solution, and that mode solutions you are getting for a particular theta m. Once you get a particular theta m, particular k1x and particular k1x will define k1 kappa 1 here, and here we are considering kappa 3 like this, and here we are considering kappa 2. So, we need to know kappa 1x, here we can solve easily and we can find out what is the kappa 2 value, kappa 3 value. I discussed earlier, I just repeat here once more. Okay. So, this is the solutions I repeat here, all these thing. But one thing you should keep in mind that your this theta m, whatever you solutions you get, that should be between theta CL less than theta m should be greater than critical angle and less than 90 degree. That I will be discussing little while later. For the moment, you do not need to consider that here. Okay. So far so good. Now, let us see what is k1 m. Here we have used k1 m. K1 m is nothing but k1 x m, k1 cos theta m I discussed, and cos theta m I can write 1 minus sin square theta m, and k1 can be k1, you know, k1 mod equal to 2 pi by lambda and can be written as omega by c. So, we are writing omega by c times n1, that is k1, and then sin theta m 1 minus sin square theta m, and then this n1 I take inside, n1 square inside the square root, n1 square and then n1 sin theta m square, and we know n1 sin theta m, n1 sin theta m, that is actually nothing but n effective m. So, I have written n1 sin theta m, just n effective m. Okay. Now, if you see n effective m, which one is higher, n1 or n effective m? So, since we can show easily here that n effective m must be less than or equal to n1. So, this one always will be positive. Okay. How that is? You just consider this one. I know this is the condition for total internal reflection in both interface. So, it should be theta CL is again greater than theta CU, because lower cladding N2 is higher than N3. So, theta CU is less than theta CL. So, if you just satisfy solution theta m greater than theta CL, that is sufficient. So, you just concentrate this one. Now, theta CL, that means critical angle at the lower interface, critical angle at the lower interface means N2 N1, that means theta CL sin inverse N2 by N1, that should be less than or equal to theta m 90 degree. So, this one I just replaced this way. Now, this is the relationship. If I just remove the sin inverse, then it will remain N2 and sin inverse, here it is coming, you are dividing, that means it will be sin theta m and then it will be sin 90 degree, and N1 also multiply both sides. After removing inverse, I just multiplied n1, n1 multiplication n1 goes. So, this side will remain n2 and this side will remain n1 sin theta m and this side remain n1 sin 90 degree, right. So, this is easy equation. So, once you get that, this n1 sin theta m is nothing but n effective m, that is what we have written here, n1 sin theta m. So, that means n effective m must be less than or equal to n1 because it is coming back from here, and it must be greater than n2. So, any solutions you are getting for n effective m, that solution must be greater than n2, but less than n1. It is, if it is greater than n2, it should be greater than n3 as well. So, that ensures the confinement. So, whatever solution, whatever wave is propagating in this slab waveguide, that should have a effective index in between. It will be less than or equal to n1, but should not be lower than n2. n2 is higher than, this is the n1 greater than n2. So, this thing, any solutions you get, any effective m or any theta m you should get, this condition should be satisfied. So, this is the condition must be satisfied. Okay. So, I have the k1 value, I can write this n effective m is smaller. So, this is a positive value. So, standing wave I can get easily. Now, what is k2x? K2 kappa 2, I would say kappa 2. Yeah. So, kappa 2 you know that is actually the imaginary, because transverse component of the x component in the medium 2, that is imaginary. We write like that, this type of solution, and kappa 2, by the way, we can solve. You remember that we could consider that, okay, since there is a tangential component, we can consider some fictitious imaginary theta t, and that theta t can be converted into using Snell's law theta m. So, we have earlier discussed this, that this imaginary part, since it is imaginary, it is a evanescent field in the cladding region. So, that imaginary part will be coming 1 minus this one, because this will be always greater than 1 when theta m is greater than critical angle. So, that is why it is also, you just multiply n2 inside, you are getting like this expression. This is your kappa 2. This is now you see n effective square must be greater than n2, that is what we have shown, that n effective m, I would write here n effective, because m is there, this should be m should be written here, typo mistake here. So, that means your this is n effective square greater than n2. So, this is a positive value, and positive value, that means I take x mod, because this side is x negative. So, I can express that this side, once you know the kappa 2 from this formula, if you know lambda, then you can calculate omega, and you can actually, if you know n effective, then you can calculate your kappa 2, then you know how much it will be stressed. So, if you know kappa 2 m, then you can say that that particular mth mode, how much it will be penetrating 1 by eth, it will be delta m, penetration depth will be delta m equal to kappa 2 m. So, for mth mode, if I can calculate kappa 2, I can find what is the penetration depth of the mth mode. Exponentially it will be decaying, right. And here you can see some kind of sinusoidal wave, and they are also exponential decay. So, you can get this type of solutions, or you can get this type of solution like this. These are the guided mode, when it is exponential decaying, but in between this will be oscillating like cosine function. So, they will be actually guided mode, and each of them, depending on their value, they will be propagating with a phase velocity. So, this is the idea, whole idea. Okay. So, we get kappa 2. Similarly, we can find kappa 3, and we can say that beyond, when x greater than d, there is a evanescent tail. So, I write kappa 3 m x minus d. Kappa 3 also same way I can write here, I can express this way, I can express this way. So, this is also positive value. So, once we know lambda, I can find how much it will be penetrating. So, thing is that you can easily find out which particular mode, if you know the effective index of a particular specific mode, you can say, and if you know of course n1 and n3 value, and if you know lambda, then you can find how much it will be penetrating in the cladding region. That is very important. Cladding region, how much it is penetrating, that actually is the important part of integrated optics, that is evanescent tail, evanescent field strength, that actually helps how much it is insulated to the neighboring waveguide or how much it can be coupled to the neighboring waveguide. Okay, that is very important. That is why I would emphasize more on this. This expression you should keep in mind all the time, and you know it is very easy to derive, as I have mentioned earlier, discussed earlier. All right. Now, all the equations, relevant equation for field distribution in 3 different region, corresponding constants, how to solve this thing, and this phi f and this thing, they are related through boundary condition, because tangential component, this is ui component. So, continuous at the boundary I can put down, I can find out easily. I leave this as your home assignment to find out what is the relationship between these things. And once you find a relationship, you can just set this one as a 1, then you can easily plot using some MATLAB program or Python program or C programming, etc., what would be the mode looking like. But one important parameter you need to solve first to see different modes, because you need to solve this theta m. For theta m solution is this one, and you can solve theta m from here, and then once you solve theta m, then you can find beta m and n effective m. Once you know n effective m, you can find out, this is m again missing here, this is also m, this is mth mode I would say, okay, missing here. So, you can find what is the kappa 2 m, for mth mode what is kappa 2 value, for mth mode what is kappa 3 m, and for mth mode what is kappa 1 m, then you can just plot and you can find out how is the field distribution can be in the slab waveguide. So, only thing is that you need to know n effective m, then you can find what is the nature easily, straightforward. So, I move on to that, how to get that. So, I just consider SOI, silicon on insulator. I just want to calculating effective indices of guided modes in SOI waveguide. That is what our next target. Once we solve that one, effective index, then we know almost all properties of a slab waveguide needed to understand the mode concepts, everything we will know. So, I know that my theta m should be, whatever solutions you get from here, that should be greater than theta CL, and since theta CL is greater than theta CU, so that means if I ensure that it is the solutions is greater than theta CL, then it is obviously greater than theta CU, critical angle in the upper interface, critical angle in the lower interface. Then I can say that solutions not only ensuring total internal reflection, also ensuring the phase condition to form a mode. So, I try to find out the critical angle for silicon on insulator substrate, where your N1 is refractive index, this one, lambda obviously you are considering around 15 nanometer wavelength, okay. And at the same wavelength, if top layer is air, that is actually 1, and bottom layer is silicon dioxide, so 1.4657. Utilizing this, I calculated what is the critical angle for lower interface, sin inverse N2 by N1. N2 I put here, N1 I put here, then I get 25 degree. So, that means anything if it is coming this angle theta m, that theta m should be greater than 25 degree. This should be greater than 25 degree or greater than theta CL. So, whatever angle it is coming to go for total internal reflection, that angle solution should be greater than 25 degree. In the upper interface, which is actually 17 degree, same thing, critical angle you calculate, it is 17 degree for silicon on insulator. So, that means if your this angle theta m is greater than 25 degree, obviously when it is hitting here, that is also theta m, that is also greater than 25 degree, because this one and this one should be same. So, if you are ensuring 25 degree here, that 25 degree also coming here also, that means which is obviously greater than 17 degree. So, that means total internal reflection will happen. So, anything this theta m less than 25 degree, that means it will be leaking something here, total internal reflection will not take place. So, if it is something theta m you are getting, it is greater than 25 degree, but less than 17 degree. That means in this range it can get total internal reflection here, but since it is less than 17 degree, it will be leaking here, upper interface. So, that time here it will not be leak, it will not leak to the substrate, lower cladding, but it will be leaking to the ear. So, you have to make sure that this theta m should be greater than theta CL and theta CU, and that calculation you can do this thing. Okay. This is fine. Next thing is that, okay, this is what I have just written down here, same thing, theta m should be greater than theta CL, theta m should be greater than theta CU, whatever solutions you get. For this condition, I have calculated 70 degree and 25 degree. Okay. Now, my intention is that how to find out this theta m solutions which satisfy at least it should be greater than theta CL. Obviously, theta CL, theta CU should be there. How to solve? Because so far we have not discussed how to solve this one. I said that this is a transcendental equation, it is not so easy to solve. Okay. I will try to show how we could solve in a graphical way. Okay. Let us see. Okay. I have written this one, this equation, I have written here, that thing simply rewritten there, this one. Okay. I just 2 m pi phi L theta m phi u theta m, and phi u theta m is this expression, phi L theta m is this one. That means lower interface whatever phase because of the total internal reflection, and upper interface what is the phase happening because of the total internal reflection, because upper interface is n3, lower interface n2, that is why this is there. Obviously, this is for TE polarization, you should keep in mind. Okay. And beta m whatever solution, this thing I have just written for your understanding purpose, and I have also shown the calculated value here to keep in mind while solving this thing. Okay. Now, you see, I just try to, you say what we could do, I can plot a figure, this axis is theta and this I can call it as a left hand side, and this entire thing I can call as a right hand side. Okay. Right hand side I have different values, m equal to 0 I can put one right hand side, m equal to 1 I will get another right hand side, m equal to 3 another right hand side, 4 any number you put right hand side is changing. But left hand side what will be changing, because for a given thickness of the waveguide n1 is fixed, lambda is fixed, so only thing is that theta m will be changing. So, I can plot as a function of theta what is your left hand side, and I can plot as a function of theta what is your right hand side, left hand side and right hand side I will be plotting. Then I can find that two curve will be intersecting in this plot, and that intersecting is the solution for theta m. Okay. That I will be getting a one particular theta m solutions. Okay. I will just for that first I will show that if you just plot only this right hand side for m equal to 0, how it will be looking like. It is shown here. This is shown here that for m equal to 0 you are considering, you just put m equal to 0, then you have phi u expression this one and phi l expression this one. And you know this thing, this two equation is valid only for theta m greater than upper critical angle, this is for upper phase, upper interface, and this one also true only if it is greater than critical angle. Less than critical angle these values are 0, no phase change happens, and exactly critical angle this thing will be also 0. Just above the critical angle a theta value, then you see the phase change happening. So, if you just consider say upper interface, this one upper interface, what is the critical angle? 17 degree. So, this is 20 degree, this is x axis, this is 20 degree. So, this is the 17 degree point. Okay. And from 17 degree if you plot, if you see that the phase is increasing as a function of theta up to 90 degree, this is your 90 degree, and it increases up to pi. So, your theta, suppose you have a waveguide here and core region here. So, that means your phase change total internal reflection starts happening starting from 17 degree in the upper interface. So, this is your 17 degree, and if you just keep on increasing up to 90 degree, then it will be seeing total internal reflection, and phase also it will be changing. Why phase it will be changing? Because of the your different component, the tangential component of the tangential component and normal component of the wave vector is going to change. That is the reason phase will be changing. So, it will be, if you just plot with a MATLAB program, you will find this rate curve. And if you just plot what is happening phase change for the lower, it will start from 25 degree, you see 20 degree, at around 25 degree it is starting. So, for m equal to 0, I can plot this one, this is actually corresponding to phi u, that is phi u, and this one corresponding to phi l. And here this is actually, we can call it as theta c u and theta c l, and this is actually theta c u. Theta c u is 17 degree, here you have your theta c l. Okay. Now, if you want to add them together, this two, this is phi u, this is phi l. So, if you add them together up to this point, you have other value phi l is 0. From here, if you add them together, you will be getting something like this. So, this one will be added here, sorry, it can be little bit clean up. So, you can say something like this, this will be like this, because this value will be added again pi, right. So, this will be your, this curve can be considered as a phi u plus phi l for m equal to 0, and m equal to 2 pi means all the data points you are getting, you have to add 2 pi more, and if you go m equal to 2, that means again you have to add 4 pi. Same curve, the curve will be shifted upward, 2 pi upward, 4 pi upward, 6 pi upward. So, this curve you can generate depending on the many set of curve you can generate just changing m value. So, but left hand side, if I just plot as a function of theta m, so how it will be looking like? So, theta m you are just changing from this one, if theta m equal to 0, this will be 4 pi by lambda, right, 4 pi by lambda n 1, somewhere you will be getting some value 4 pi, this means 6, lambda 1.55, so 12, so it is more than 10, somewhere here you will be getting, maybe here, then you will be getting something like this. So, it will be your left hand side like this, it is a cosine function, right. At theta m 90 degree, it will be 0, and theta m 0, it will be 4 pi, somewhere this one 4 pi by lambda n 1 d. So, that will be the value at here, and it will be there. And where this left hand side and right hand side crossing, right, for m equal to 0, you will get that value theta, that will be your theta 0, right. So, you are getting m equal to 0 value, theta 0 solutions you are getting. Now, this curve, if you add 2 pi, then what you will be getting? 2 pi, maybe you will be getting 6 pi, somewhere here you will be getting, and then after 2 pi adding, again that curve will be added. So, you get another solution there. So, that is clearer here. So, if you just show that, maybe it is better to look into it. Yeah. So, this is solved for right hand side, that means this one right hand side for m equal to 0, that this curve, that means m 0, this one 0, I am adding this 2, then I get this curve. Okay. Just use this curve and this curve plus, and then you just plot, and then m equal to 1, you see, you have to have, I think what happens in this curve, it's supposed to be 2 pi means 4 pi, but here you are adding just 3 point something pi you added, that is because this 2 term is cancelled. So, 2 cancelled here, and this is 2 also, that means this one actually calculated for phi u total divided by 2. So, half it is plotted, it is not phi l theta m, 2 is not multiplied. So, left hand side also this 2 not multiplied. So, that means this value is nothing but 2 pi by lambda n 1 d. D is the thickness of the film, that one is this one, and this one is basically phi l plus phi u by 2, that is whatever value divided by 2 it is plotted. So, you see, if you are just adding m equal to 1, then you get this plot, and m equal to 2 you get this plot of the right hand side for m equal to 1, right hand side for m equal to 2, right hand side this one for m equal to 3, and left hand side you are just putting 2 pi by lambda n 1 cos theta, this thing you are plotting. So, you get a one solution here and here and here, this value you are getting one solution, you are getting one solution, here you are getting one solution here, and for this calculation you have considered d equal to 1 micrometer. So, if d equal to 1 micrometer, if you are considering these solutions you are getting, this is for m equal to 0. So, whatever solution you will be getting, that is actually theta 0, and this solution you will be getting theta 1, this solution theta 2, this solution, this is actually critical, this is actually what, this is 25 degree, this is actually theta CL. If you add one more for m equal to 4, you get a solution somewhere here, another 3 if you add here. So, it is 9 point something. So, somewhere here you will be getting, and that solutions you will be getting, which is actually theta 4, you see this theta 4 is less than theta CL. So, this solution is not acceptable, that will not give you a guided mode, fine. So, it is actually it's a very easy way, if you just use a MATLAB numerically, you just can solve all this theta naught, theta 1, theta 2, theta 3, and once you get them, so you can find your so called n effective m, you will be getting, for example, your say n effective n 1 sin theta m. So, all the m value you can enter, then you can get n effective 0, n effective 1, n effective 2, n effective 3. Since theta naught we have solved there, theta naught is greater than theta 1, greater than theta 2, greater than theta 3. If you just go back to the previous slide, so theta naught is greater than theta 1, this one, right, theta 1 greater than theta 2, theta 2 greater than theta 3. So, higher order mode, your theta value will be reducing. Okay. So, if that is the case, so we can say that n effective naught will be greater than this one, because that value is this one, theta naught is higher. So, this one and so on you will be getting, right. So, in this way you can find a solution when actually n effective is exactly greater than some value, exactly is n 2 or slightly higher, that will be the highest order mode, that can be supported by the slab waveguide. Okay. Now, so we know now how to calculate n effective. Once we know how to calculate n effective, you can find out what is that kappa 1 and m, and what is that again kappa 2 m and kappa 3 m, because they actually involve in the field distribution we have shown earlier. If you just go back here, I just discussed here, you see this kappa 3 m, kappa 2 m, kappa 1 m, they all are actually n effective dependent. N effective, once you solve, then you get all the parameters, and then you can find out how it will be distributed, how exponentially decaying in the top cladding, bottom cladding, and how would be it is actually sinusoidally. So, you can easily plot your electric field. So, you can try that, you can solve, give certain value of d equal to 1 micrometer it is given, you can use 1 micrometer and try. You know that for 1 micrometer you get 4 solutions for T polarization. You can get also similar type of solution for TM polarization. So, if you are 1 micron thickness, you are dealing with 1 micron thickness of the SOI, then you can say 4 different modes for T polarization, 4 different modes for TM polarization. But normally, you know, these are the general discussion, but most of the time you would be interested to have a you need to have a single mode guide. So, in that case what to do? What you have to do? You have to do, you are just getting this value, this curve, that is the left hand side. If this left hand side can be reduced downward, suppose you are getting something like this, something you are getting like this. So, you get only one solution, one solution here, below one solution below the above the critical angle. So, if I reduce this value, how we can reduce that? Either I can reduce N1 or increase lambda or decrease D. Since material platform N1 is fixed, lambda is fixed, what I can do? I can reduce the thickness. So, if I reduce the thickness, slab thickness, then you can ensure that okay, it can be designed for just one mode in vertical direction, x direction. Okay. That is why the D value typically it is used 220 nanometer. So, that vertical direction you can at least you can confine only one mode, not more than that. If it is more than that, then actually it will be multimodal, at least vertical direction. So, that is the reason all the foundry and silicon photonics industry, photonic circuit, everything they are fabricating with a SOI device layer thickness of around 220 nanometer or less than that. We can show that even less than 220 nanometer, even 45 nanometer thickness, 30 nanometer thickness people also demonstrated single mode waveguide in the vertical direction. Okay. Now, next thing very important. So, I want to learn that okay, we have a slab waveguide and we have a discrete solution for theta naught, theta 1, theta 2 and theta 3. These 4 solutions are there for D equal to 1 micrometer for example. And there basically you can find out the solutions are theta naught is about 80 degree and theta 1 equal to 70 degree and so on you are getting. So, I would like to know when I am launching light, suppose you have somehow diced here vertically clipped the substrate, this is your device layer SOI and this is silicon dioxide, below will be substrate and air. Now, you just cut this point and polished and you want to launch a light. You have 4 different modes it can support in T polarization, TM polarization is also another 4, but I want only to excite a theta naught, which actually even though it supports more than 4 modes, but I want to excite only theta naught. Then I can ask you a question that what would be the angle of incident here in the outside from here, so that you get exactly theta naught. With this example I try to give you a very good calculation that what is the maximum possible angle you can have, so that this angle will be exactly critical angle. So, you are making an incident here, this is your interface, this is your normal and this is incident wave and this is your transmitted wave. So, here angle is theta A and if it is 17 degree critical angle, this one only this one critical angle, then this one will be 73 degree and here it is N1 and it is AR, right. So, what I can do, I can use a Snell's law. If you use a Snell's law, that means in AR refractive index here is NAR, NAR sin theta A equal to N silicon sin 90 minus theta Cu, this is theta Cu, 90 minus theta Cu, that is 17 degree. So, here in this case N1 is silicon, N silicon is nothing but N1, nothing but this one that is coming here. I put down, I get this value I get, because sin 73 degree is about 0.9563. If you multiply with a N silicon, then you get 3.325. It is a simple calculation, but very odd. If you see N air is 1, then sin theta A, whatever you are getting, sin theta A is equal to 3.3258, which is greater than 1. Sin theta greater than 1, that means theta A must be imaginary, sin theta cannot be greater than 1, must be imaginary. So, that means this is the angle where I can have critical angle, this theta A, exactly critical angle, which is coming as imaginary. If theta A value less than that, then only if it is less, then 73 degree will be less this instead of 73 degree it will be less. So, if it is less, then it will be more than 70 degree. So, suppose it is 70 degree. So, this will be 20 degree then. If it is 20 degree, that means more than critical angle. So, here total internal reflection can take place. So, that means whatever solution I am getting here, that is actually, that should be something the maximum possible theta A, and that maximum possible theta A is absurd, imaginary. So, that is the reason actually at any angle you just go from the incident, that actually create inside it is greater than critical angle. If you are, of course, if you are not grazing exactly, little bit angle if you are giving. So, whatever angle it is coming here appearing inside the crystal in the device layer, that will be greater than 90 degree. So, basically this theta A is you can consider as a 90 degree, this exactly 90 degree is the theta, that is acceptance angle. So, because of the very high refractive index of the silicon device layer, your acceptance angle is very wide. So, anywhere any angle if you just launch, light can be coming and total internal reflection can take place. Same argument is true if you are just considering the other side also. So, here theta A prime also, this is coming also here in this calculation, if you see it is also coming greater than 1. So, it is something that anywhere this side or this side, anywhere any direction you sign, so that will satisfy your more than critical angle in both interface, and that will be guiding. So, that is very interesting, easy to couple light inside the silicon device layer. Okay. So, that is why we say that any angle of incident, that is theta A, that is 0 to 90 degree, results into total internal reflection at the lower interface. And so, finally, we can say that any angle of incident of theta A and theta prime results into total internal reflections at both upper and lower interfaces. Okay. So, I can launch any direction, it can be satisfying one of the solutions you desire, theta naught, theta 1, theta 2. So, you do not need to bother, that solution can come theta A, this incident angle, that can be anywhere it can be, but total internal reflection can take place. That particular angle ensure total internal reflection, but may not ensure the solution for guided mode. Guided mode solutions, whatever way we discussed, that has to be followed. Hopefully, you get an idea how a slab waveguide works. I have taken example of silicon on insulator, but any slab waveguide, you consider indium phosphide slab waveguide, gallium arsenide slab waveguide, lithium niobate on insulator slab waveguide, silicon nitride slab waveguides, the principle same, you can calculate and you can design your how many modes will be there depending on the thickness, how many modes it can be supported, and what would be the minimum thickness required or maximum thickness required, so that you can vertical direction only one mode it can support. If it is one mode it is supporting, whatever angle you say you sign, if at all it is guiding, that will be fundamental mode, because other mode even if it is excited, that will be leaked, that will not carry energy, propagate as a mode. So, if it is a single mode, I can ensure that that particular mode has a fixed phase velocity. So, I do not need to bother about that. Okay. But if it is a multi-mode, different modes are there in the slab waveguide region. So, all the modes will travel with a different phase velocity. So, that is called modal dispersion. So, that is a problem for designing devices, but this is something ground level work for understanding guided modes in slab waveguide. And then we will be discussing same approach. I will be just considering how to design a 2D waveguide, 2D confinement, and what would be the possible solutions. And then I will discuss that if there is any limitations or not, and if some limitations are there, the alternative path we have to consider for understanding more rigorous photonic integrated circuits, more complex photonic integrated circuits. With this I stop here. Thank you very much.